Okay, so we're going to start looking at module number 5, which is tolerances and fits. And as we look at module 5, you'll notice kind of that same stuff that we've been seeing in our Canvas shells. The first one is going to be our learning plan. The session recordings are going to be on the next folder here. And then we have practice problems and an assignment. The practice problems we're going to be going over here today in class. And then there'll be some applicable application problems that you should be prepared for after doing our practice problems. So I'm gonna go up to the learning plan first. You'll notice that we have a PowerPoint presentation here that we're going to be using to guide us through our chapter. We're going to be doing a couple of practice problems. Those you will be handing in. And then we will be utilizing in our second practice problem, the Force Fits Excel spreadsheet. So feel free to download that so you can follow along. Now, I am going to click on our tolerances and fits, and this is going to be our guide through our chapter. All right, so chapter 13 is where we're going to be looking here. This is the chapter right after shaft design, okay? So you are the designer. So I want you to open up your book to page 547. And it's going to sound familiar. You're going to be the designer responsible for designing a double reduction gearbox. And if we look at figure 13.1, which is right underneath here on page 547. This is the You Are the Designer section, okay? It's really just wanting you to reflect on the design that you would have created. Now, here we have a double reduction gearbox, a little bit different orientation than what we looked at, but still very same type of elements, identical elements, shafts and bearings and gears. That were designed in to, meet the needs of whatever this is going to be doing. So as we kind of read through this section, and I'm not going to have you read it, once we have everything kind of put together and designed, and we've done a little bit of this work already, but one of the biggest things that we need to think about and to go back and to refine is going to be the tolerances on each and every one of the features, looking at how they are going to be working, how accurate they need to be, or maybe how not accurate they need to be. Additionally, that they are manufacturable. Okay, so that's what this chapter is dedicated to. And it's looking at manufacturability. It's looking at those tolerances, the types of tolerances, the types of fits. When we get into things like, for instance, force fits or press fits, those are going to be stresses that are going to be induced into the material. We have to check those to make sure that they are not exceeding what the material can do. So those are the types of things that we're looking at here. Now, what I'm going to do is I'm going to kind of bring this forward again. So some of the parts in our assembly, the vendor specified for us what we were supposed to do to incorporate them. So for instance, the bearing manufacturer said what the tolerances were on the bore and on the outside or for the housing, right? To put on the shaft and into a housing. The retaining ring manufacturer told us, this is how wide you make that groove and this is how deep you make it, right? And they even gave us the tolerances that we would want to apply to it. So in some cases, that's going to be set for us. And we need to then adhere to that so that we ensure that our elements are going to perform the way we're intending and the way that the vendor, if you would, promises that they will. But others, you as a designer will be picking and specifying those. So for instance, we did look at the gear bores to the shaft diameters, okay? And we looked at the description of some fits and we put some tolerances on there from the RC fits that seem to line up best with our application. Same thing for keys and key seats. Although that was specified out of the machinery's handbook as standard, you still have control over that. You could change those if you so chose to have a little bit different range, okay? Now, you as a designer will also need to consider the following when you're preparing your documents, meaning you're going to be responsible for creating good, accurate, to the standard details and assemblies so that the parts can be manufactured. Okay, so that the parts can be manufactured. So you need to look at those locational elements, that they're going to match the function of the part, and where like dimensions need to be held, that they are positively being held and going to always be there. You need to ensure ease of assembly and service. If there are parts here that could fail, you want to have the ability to get at those easily so that whoever is fixing it, whether it's the customer or maybe a service tech, that they're not having to rip everything apart to try to get to, what they need to change. We all know, when we take our car in to get a repair, so much of the cost is not so much in the parts, but it's in the labor and it's in the time that it takes to get at whatever it is. Now, in some cases, it's inevitable, but if we as designers can take into consideration that assembly and service, you really, can do the people who are dealing with it later on a lot of favors. The manufacturing process capabilities, this is huge. Gone are the days when we have all of the manufacturing processes under one roof, okay? In some cases, larger companies have the ability to have the manufacturing, at your fingertips, but many times we are sending out our designs and they are making them, and then the parts are coming in to be maybe assembled at our facility or another. It just kind of depends on how the company is structured. So you as the designer are responsible to make sure that, again, your details and your assemblies are taking into consideration manufacturing processes and their capabilities, okay? Surface finish, that's another one that if you need a certain surface finish, especially when we have things that are mating or things that have to seal, we need to specify that surface finish so that it's going to be appropriate for the final function. Relative cost, okay? When we're putting dimensions on parts, it's not just a pretty picture. It's not just 3 place decimals. It's thinking about how this feature is going to be made in manufacturing, and then making sure that whatever tolerance level you put on it is going to cover the manufacturing process you're thinking that it's going to be. Those who have had manufacturing experience, whether it's, working in a shop, whether it's assembling, making parts, working in a machine shop, welding, any one of those things, they understand intimately what the capabilities are of that process. So if you have some of that experience, use that as a designer. You're going to be better for it. But if you don't have that experience, it's also important to be able to go down to the shop floor, talk to somebody who does have that experience, ask them, how would you set this part up? If there's really no, place where your function-wise need to set up a 0-0, ask how they're going to make it. People are going to appreciate, having input on your design, okay? And there's nothing wrong with, especially when you're new, asking for help on that, okay? I can't stress that enough, because your cost of that part, or the cost of that part, is going to be directly related to the tolerances that you put on a drawing. Those tolerances dictate the manufacturing process, which then dictates the cost, okay? Additionally, stresses are going to be produced in these parts, especially when there's an intended interference fit. Sometimes we want to press these parts together so that they don't come apart again, and that's how they're going to be held in place. That's totally valid and acceptable, but we have to also calculate the stresses there so that we're not exceeding what these materials can do. Because if we go beyond their yield point, we know that at that point and beyond, they're no longer structurally okay in internal to their material. And they're not going to, perform and hold as we had intended. So we've got to check that. And then also we have to decide, is there going to be heat or cooling needed to assemble, especially in these heavy interference, types of situations. Maybe just pushing them together is not going to do it. We actually literally have to heat something up to expand it, or cool something down to make it smaller in order to put them together, and then let them heat up and cool down to stay together. So those things are all on you as the designer, which is super important. You're a very important part of the way that a company works, but also it's pretty cool that you get to have all that decision-making process, or realize that how you do things is going to directly affect all of these items. Okay, so exciting. So our objectives of this chapter are going to be looking at these tolerances, production processes, the costs, how they're related, the factors that you're going to be taking into consideration when you're choosing tolerances and fits. We're going to be looking at, you know, what are these preferred basic sizes? We've mentioned them here and there, and maybe you know what they are already, but it doesn't hurt to bring those back into the front of our minds. We're going to review clearance fits, interference fits, transitional fits, and also locational fits. They're not listed here. And then probably the bulk of what we're going to be doing is looking at, okay, when we have those force fits, what are the stresses that are going to be induced in the parts, and making sure that they don't exceed those yield points of the materials. And then at the very end here, there's a little section on general tolerancing methods. Okay. Now, at this point in where you're at in the program, you have had, you know, creating models, creating drawings, creating assembly drawings, and using the standards. This is another application of, so nothing that we're doing here or talking about goes outside of that. Additionally, you had GD&T where you would have talked intimately about these things. Okay. So this is just one little reference here, but it's a reminder of, but the one thing that you haven't done yet throughout the program is calculated these stresses. And that's going to be, you know, towards the end of what we're going to be looking at, but we want to make sure that we're all on the same page as we arrive here. So these things we're going to be reviewing here at the beginning. So tolerances, production processes, and costs. This is our next section here. This section starts, if you want to follow along in the book, on page 548. Now, in this section, they talked right away about total tolerance. Okay, total tolerance. So the total tolerance that any particular feature has is going to be the difference between the maximum and the minimum permissible dimension. You have direct control over this as the designer. Why do we need to tolerance drawings? Why do we even put tolerances on things? Why can't we just give it a number and that's it? Tell me why, if you want to put it in the chat or if you want to verbally do it, you're good. So why do we need tolerances?
I actually just went through this at work. Sometimes you need a tolerance because you're trying to create a ceiling surface, for instance, and when you don't put a tolerance on, the machine shop making the part doesn't know what the acceptable range of size is. So when you go to put said ceiling pieces together and they don't fit, you can't say anything to the machine shop because you didn't spec out how far out of your stated dimension the part can be.
I sounded like that was Mitchell, and I'm so sorry, but is there a chance that maybe Ryan, you could repeat or review what Mitchell?
Yeah, can you hear?
I can hear
you hear me
very
okay?
well. Yes.
Okay.
I know in the classroom it might be harder.
All right, yeah, Mitchell just said he went through a current example at his job where
Mhm.
there was a part in the machine shop that didn't have specs on it,
Yeah.
but it was a ceiling surface. And essentially there was nothing to hold the shop accountable for the requirements on that because there was nothing on the drawing, right? So then the part wasn't made as intended, as designed. So if there would have been tolerances on there saying, you know, surface finish and
Mhm.
specific tolerances for the dimension, then it could have functioned for that ceiling surface. Is that about right? Yep.
Perfect. Yes. No, that's an excellent example. We do need them because, you know, like Mitchell pointed out, otherwise nobody knows what you really want. They kind of take a stab in the dark, and more often than not, it's not going to really be what you need, right? Perfect. Okay. Yes. So we need those limits. Eric just put in the chat, unlike us, the people, machines, tool making, these are not perfect, right? There's a lot of variation at every step of the way. So when we get material in, that material, you know, depending on the batch, is going to have, you know, a little bit different chemistry from maybe a month ago when we got it. So all of a sudden, it's not as easy to machine, or it just reacts a little bit differently. The time of the year is going to be a variable that we're going to have to deal with. And depending if it's, you know, the summer when it's warmer and you don't have an air conditioned shop, all of a sudden the parts are going to be on a different side of your tolerance level than others. Machines, depending on how new, how old, how capable they are, right? tools can wear out. There's a life to those as well. So all of those variation, we have to deal with that, and tolerances are exactly that. And again, the difference between those min and those max values, that is still going to allow something to function. Yes, 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 yes. Other reasons, any other reasons you're thinking of that tolerances are essential, and why we have to make sure that we're thinking about each and every one on our drawing?
So things fit properly.
I think I heard so things fit properly, right?
Yep, BJ
Yes,
said
And
that.
yep, and that speaks right to the actual function of why we do it, right? That's our responsibility as the designer. We have to make sure that it's gonna properly fit, it's probably gonna function, but we also have to take all these other things into consideration at the very same time. So it is not a small task that we take on. So yes, function is one thing, and making sure that it fits, but now is it manufacturable, or are we gonna put the tolerances on appropriately so that everybody understands them, right? So, so yeah, that's good too. Any others that think people are thinking of? I think those are good. I think those are good. All right, so let's go to the next slide. Unilateral and bilateral and limits. So when we put tolerances on a drawing, they're going to be specific to a feature. So it's going to be the size of a hole. It's going to be the, distance from one edge to the side of a cutout, all the things, right, to make. And the tolerances that we're going to be putting on come in a couple different variations. The first one here is called unilateral. Unilateral tolerance is when we have all the tolerance on one side of the basic dimension. So for instance, we could have a 1-inch dimension plus 10 thousandths minus 0. Okay, so that means the minus 0 means that all of our tolerance is going to be, above 1 inch. So our smallest dimension is going to be 1 inch. Our largest dimension is going to be 1.010. So 10 thousandths is all the tolerances on one side. And it could be on the opposite direction too. It could be 1 inch plus 0 minus 10 thousandths. Okay, but unilateral just means it's on one side or the other. Bilateral tolerance. This is where we have deviation on both sides, and we can either have equally distributed or equally distributed, or we can have unequally distributed. Sorry. Equally is going to be, as we see on the top there, that same 1-inch dimension, but let's say if it's defaulting to our tolerance title block in our drawing, a very common one for 3-place decimals is plus or minus 5 thousandths. Now, I want to iterate there. When we have a title block tolerance that we're defaulting to, make sure you know and understand it, and it never changes. So I've had designers ask me this, and I've had them actually do this in class, where they're like, well, I actually want my 3-place decimal to be plus or minus 8 thousandths for this drawing. And I'm like, no, we can never change that. So once it's adopted by a company, that is like you cannot change that. That's sacred. Okay. If you want anything other than a title block tolerance, then you are going to be specifically putting it behind the tolerance or behind the dimension up in the drawing. Okay. So equally distributed is going to be something very similar to like a tolerance in a title block, or it can be plus or minus 1 thousandths, but it's going to be the same amount top and bottom. Unequal distribution is going to be where we have a little bit on either side, and it doesn't have to be the same number. So just as an example here, that 1 inch plus 10 minus 5 thousandths. Okay. And then we have more on one side than the other, but we have some on each side. Okay. So, so any questions about the different types here and how we can, change it depending on what we're looking for? All right, I'm certain along the way, I haven't had you guys for the CAD classes, and that's totally good and fine. Those I know have come out. And so this is again, review. Now limits. Limits are going to be the identification of the actual min and max dimension as determined by our tolerance. So if we go to this very first one here, the limits are going to be 1.010 as its max and 1.000 as its min. A really good practice is when anything starts to get more critical, put your limits on. So when we start looking at, dimensions that are, small little numbers. So if we're like plus or minus, 1 thousandths, or you're getting into 4 and 5 decimal places, always put the limits. Don't leave it to the plus or minuses, because you're inducing human error into that process. And even if it's something that you're like, oh, that's not hard to, add and subtract, it's a decimal, and that can make a world of difference when we're dealing with really accurate parts. So limits are always a good thing to do, especially if there's a chance that, a mistake could be made, and the mistake could be, critical, and it could scrap a part. So limits, again, are just that identification of the highest and the lowest value as determined by the dimension. And we can put limits on a drawing for a part. Again, when it's critical, it's a good idea to do that. Now, allowance. Allowance is the intentional difference between the maximum material limits of mating parts. So there are two different types of allowance. There's clearance and there's interference. And when we determine the difference between the two, clearance is always going to be what we end up with, a positive allowance. So it's going to be a positive number. Interference, on the other hand, is going to be a negative allowance, because when we do the difference in the maximum material conditions, parts of each one are going to try to occupy the same space. That's what an interference is. Okay. Allowance is going to be that looseness or that tightness. And also another way that we call this out just below here is going to be the fit that we're looking at. Now, the fit can be one of 4 different classes, and the fits can be a clearance fit, or a running clearance fit as we call them, interference fits, locational fits, and transitional fits. Okay, so a clearance fit is when we always have clearance. Okay, there's always going to be a difference. Now, we can have very close clearance where there's not much at all, like when we were talking about, and we applied the tolerance to the bore of our gear to the diameter of the shaft where it was going to mate. We wanted those to be, we want to be able to get them on freely, but we didn't want them to move around a lot. So we didn't have much clearance, max or min there. When we have an interference fit, that means that our allowances, when we put them together, there's not going to be any wiggle room, because they're literally pressed together, and both pieces are trying to occupy the same space. Okay. And an interference fit is an intentional okay fit to have, because there's things that we want to do that with. For instance, when we put bearings in place, that's an interference fit. A locational fit is going to be one where we have a clearance fit, but it also can transition over to like a line-to-line contact, meaning it's just on the line or a little bit of clearance. That's called locational. Dowel pins are going to be locational pins, or going to be locational fits, because they're for exactly that. Usually it's trying to line something up before we tighten it down, but we want it to be in good location. Now, a transitional fit is very similar to locational. It's where we have a little bit of clearance, very little, and then a little bit of interference on the other side. So again, there are, locationals can be these transitional fits as well, where we maybe tap something on in some cases, or it does go on, but it's like, oh, we can feel that line. So these are going to be, for some specific locational types of items. Our most populars are the running clearance and the interference. Now, our tolerances, production costs, or production processes and costs. So as we said earlier, oops, this might have been allowance is going to be that intentional clearance and interference. And once we decide what our fit is, it's going to also dictate the number of decimal places that we have. Now, the cost of the part is going to be driven by that tolerance, meaning if the difference between my highest value and my lowest value is a small number, my cost is going to be high. Okay. If it's a larger number, the difference between the high and the low is larger, it's going to be lower cost. Or another way we can think of this is when we look at a small tolerance, so the total tolerance that we're going to allow on that part to function, if it's a small target to try to hit, it's going to take longer to get there. It's going to take more operations. It might take more time. It's going to take more expensive equipment, because we have to have capability there to hold a tiny, tiny tolerance, something that's small. And the smaller that tolerance is, the more cost is going to be induced. It's going to take longer. Like I said, it's going to maybe take somebody that's more skilled to actually, make it. So a large tolerance, on the other hand, if we have something that's wider and if you think about it as a target, we've got, you know, a wider target to hit. Now, all of a sudden, it doesn't take as long to get to. We can achieve it faster. We can do it on less capable, more cost-effective types of machines. The person, you know, maybe making it doesn't have to have a lot of skill and expertise. So they aren't as expensive, if you would, to make that particular feature. You as the designer, again, have direct control over this. Each and every dimension that you put on a drawing, you want to think about, is the tolerance that I have on here appropriate, number one, for fit and function, but number two, manufacturability. Is it that critical that I'm only going to be able to make it on this, that, or the other machine? Okay. Or on the other side of it, if you put a 3-place decimal on something and it defaults to the title block and it's plus or minus 5 thousandths, and it's maybe the length of a cover, does it need to be within 10 thousandths? Could you do it maybe plus or minus 20 thousandths to make it to 2 decimal places? So each and every one of those dimensions is going to, you know, correspond to not only, you know, can it be made, but what is it going to cost? Okay, so a good designer will literally think about each and every one of those dimensions. It's not a matter of SolidWorks or Creo puts all my dimensions on and now, oh, it's done for me. No. You are the human. You have the brain. You have the know-how and the knowledge to make this decision here. And this is directly related to what you do. Okay, and that's a really, really important part of the design process. So as we look here, the next thing we're going to look at is tolerance grades. Tolerance grades are going to be the tolerances that are produced with approximately equal production capabilities. So you're going to notice here that we have a number of tolerance grades in the inside here, and they go from 0, 1, all the way up to 16. Now you'll see on each one of these lines, we progressively go from a very accurate, you know, type of tool, a measuring tool, so a micrometer, calipers and such. And we go up to more rough forms like castings, sawing, or forging, you know, or parts that would have been forged. And as those numbers get larger, that means that the tolerance grade or the tolerance level is also going to get larger, or my target is going to get wider. My target is going to get wider. So things that are machine fit are going to be on this line right here. Okay. Materials that are supplied that come in are going to be here. And then rough forms, like it says here, castings and sawing. And then on the very top, these are going to be really accurate, you know, machines and items that are going to need a very small tolerance. So small tolerances up here, high cost, low tolerances down here, very low cost. Okay. Now tolerance grades, or tolerances, tolerances for some tolerance grades. Now notice that the note here says tolerances in thousandths of an inch. So that means, like we did last week when we looked at the RC fit for the bore in the gear to the shaft diameter, we have to move this decimal place to the left 3 places. So it would be 1, 2, 3, okay, on each one of these. So as we look here, you're going to notice that as our tolerance grade gets larger, our value for the tolerance is going to also get larger. So at the end of our chart here, our largest numbers for any one of the sizes at the left-hand side are going to be our smallest numbers. So a tolerance grade of 4 is much more accurate than a tolerance grade of 11, okay? You're going to notice here as well that as we look at nominal size, small parts are going to have the ability to be held in tolerance more accurately than larger parts. And that's just going to be, you know, due to the sheer size of things. There's, you know, a lot of different variables that go into that, but it's going to be harder to hold tolerance on really large parts. So if I have a really large bore that I'm trying to hold, or, you know, I'm trying to mill something out like a cutout and it's going to be on a large piece, they're harder to hold than smaller ones. Now, I just want to, before we move away from this chart isn't in my PowerPoint, so I want to go back because it helps us understand these grades. So I'm going to go underneath my camera here. On page 549, there are 2 charts here that are really, really important, and they help to kind of make sense of, you know, some of this manufacturing process stuff and such. Now, we've briefly talked about or mentioned surface finished, okay? So when we look at surface finish is going to be in micro inches. You're gonna notice the horizontal axis here is in micro inches, and this refers to the surface finish. When we look at surface finish, we're looking at, you know, the peaks and the valleys that are on a surface after we use a certain manufacturing process. So if I'm, for instance, and I know it's hard to see on my overhead here, but if you look in your book, right here, a micro inches of 2,000, you know, peaks and valleys, 2,000 micro inches, that's going to be, it's a large number, as you can see, compared to the others. That's going to be a flame cut, a forged, an as cast, a sawed finish. Okay, we know what a saw looks like. When we cut metal, we can literally see all of the, you know, the saw marks that go down. That would be like a 2,000 finish. Okay, a 2,000 finish. As we move to the right here, you're going to notice that the numbers get smaller. So micro inches wise, the peaks and the valleys are getting more shallow, which means that the surface is getting smoother. So going from left to right here, this is rough, and this starts to get smooth, smooth, smooth. Okay. Now, 125. 125 is an important number. 125 is what most all machined parts will hold, and very run-of-the-mill, you know, machine shop types of equipment. So milling machines, lathes, drill presses, and even saws. There are saws that'll hold a 125. Okay. And a 125, again, micro inch just means that this is going to be a milled surface, one that we've rough, probably, you know, cut or milled, but then we go back over the top of it and we take a cleanup cut, and we've got a 125. Okay. When you were down in the machine shop and you were doing your cold processes class, I am certain you did a 125 finish and kind of looked at the differences between, or a rough cut as opposed to a finish mill. Okay. So 125. Now you'll notice that this chart right here looks at the cost of manufacturing on my vertical axis. Okay. And you'll see it to our surface finish. And you'll see something that happens right at that 125, or I should say right after the 125. Do you see how all of a sudden we steeply go up when we want to get to the 63? Okay. This is where, like, down here is kind of all the basic manufacturing processes in a run-of-the-mill normal machine shop. I don't know what normal machine shop means, but, you know, like I said, mills, lathes, drill presses. Once we start bumping up here to the 63, this is going to be a finished turn. This is going to be where we start looking at, you know, 2 and 3 finish cuts on something and taking more time, having machines that are more capable of, you know, achieving this. Okay. So if we go down and we correlate this 125 to what's going on in the bottom figure, here's our micro inches again, across the top. Here's our 125. I'm going to use my highlighter. I'm going to go down the 125 line. Notice that it touches these horizontal bars. Each one of these horizontal bars represents a manufacturing process. Okay, so now flame cut is over here. But when we start to get to forging, at the high end of forging, it can achieve a 125 finish. Sawing, as you can see here, can achieve a 125 finish. Drilling, chemical milling, discharge milling, regular milling, broaching, boring, so that's at the start of it, turning. These are all of those processes that in a machine shop are readily available. That's why 125 is a big deal, okay? Anything above that, now we've taken out some things, okay? Now we no longer can forge, okay? What else did we take out as we went across? Maybe, some of these machinings, drilling. Once we get to 63, drilling is probably not what we're trying to achieve on a 63. Anything that's on the very edge here, probably not going to really try to approach that, okay? So if we want to get a 63, then notice that we have to go down to some other options. Broaching, boring, turning can get it. But then we've got some other things here like grinding and honing and such as we continue to work the way over here. But then also look at how after 125, It doesn't take long, and we are going up, up, up in cost. Many times when we start getting into these grinding and honing and lapping, a lot of regular manufacturers don't have those. You're sending those out to somebody who's going to do that for you. Okay. And all of that induces cost, because now I've got to wrap my parts up. I've got to ship them out. I've got to wait for them to come back, and then I've got to bring them back in. I've got to inspect them. That's all time, and time is money. Okay. So when you can live in the 125 or in the capabilities of those run-of-the-mill machine shop type of operations, you are going to be in a golden place as far as manufacturability. Now, am I saying you can't use those other things or you can't go beyond that? Absolutely not. But always have it be your first consideration. Okay. So as a good designer, manufacturability and cost is what you're very responsible for. Okay. Now I know that's not something new that you've ever heard. So again, just reviewing. The next thing is preferred basic sizes. Okay. I've mentioned this as we were looking at our gearbox project, but preferred basic sizes are going to be dimensions for which your tolerances are applied. But more importantly, they're dimensions that are going to fall in a place that is, part of a standard. So if we go to Appendix 2 in our book on page 782, you're going to see that there is a nice chart that lists all of the basic sizes. 782, get there first. For both metric, I put the wrong page. I'm sorry. It's 784. I'm gonna go back underneath here. So the chart that I'm referring to is Appendix 2, but it's on 784, not 782. Okay. And what you'll see here with this chart is that this is the preferred basic sizes. Now, for fractional, okay, for fractional inch, we want to try to get them to the closest like fractional increment. And for smaller sizes, it can be in 64, 32, 30 seconds of an inch increments. As we get larger, you're going to notice that they space out further and further, okay? When we start looking at decimals, these are the inch decimal increments that, seem to be the ones that people land on. And in a lot of cases, they correspond to many of the fractional inch. And then lastly, the SI or the metric units, here are the ones that are the preferred sizes for those as well. You'll notice again, as you're in the smaller sizes, you've got, more increments, but then as you get into the larger ones, it gets further and further apart. So you don't want to, for instance, if I have 1 3/4, if I'm coming in at 1.72, well, rather than using 1.72, it might work design wise, but your basic size, you should go to the closest basic size. Okay, basic size. Does that make sense to everybody? We talked about that in our gearbox project, but those are things that when you get out in industry, you're going to really want to pay attention to, because tools, and I know that this came up when we were talking about this, tools are made to these basic sizes depending on the units that you're working with. So in English units, most all of our drill sizes, our bore sizes are going to be made using the English increments. Same thing with metric. If you're going to be making something that's metric, it's going to be on those metric basic size increments. So adopting those and knowing those is really important. And then having a list referring back to those is there for you. Now, the next section we're going to look at is we're going to start looking at specifying some fits. Okay. So, so the first category that we have here is the one that's, like I said, we looked at this one when we did our gear bore to our shaft diameter, and clearance fits are going to be some that we use on a regular basis. Now, they're designated by a standard, so an ANSI standard B4.1, and there are 9 official classes. Now, these 9 official classes, you can see the descriptions and the charts for each one of these in the machinery's handbook. Okay, as you know, there's a couple in the lab, but you can also find these online. But we have 3 of the running class fits listed, the 3 common like sections of it. So if we go to page 551 in our book, at the top here of page 551, you'll notice that they have RC1, RC2, RC3, RC4, all the way to RC9, okay? And they give a brief description in parentheses there, but then even a little bit more, you know, as you go along. So RC1 is going to be the closest fit. RC9 is going to be the one that's going to be the loosest with the most amount of slop, okay? And then we've got all the different categories in between. You'll notice that the charts that we have here, which line up with the standard, are focusing on an RC2, an RC5, and an RC8 to just kind of grab a couple and, you know, not take up too much space in the book. So when you're doing your assignment and when we are looking at our example, we'll go to this chart to pick it out. Okay. Now, these charts are all going to be in, again, thousandths of an inch. So at the bottom here, it says limits are in thousandths of an inch. So all of these numbers where we see a decimal, we would actually move them 1, 2, 3 to the left for their actual value that we would apply plus or minus to our basic size. Okay. So when we do our example, we'll go over how to use this chart in detail. Basic hole system, basic shaft system. So basic hole system, this is used for I would say 99% of all the fits. Our charts are made to what we call the basic hole system. Basic hole system means that we are putting the basic size on the hole. So if it's a 1-inch diameter, so like, as you remember for our shaft design and our bore and our gear, the gear got whatever that basic size was, whatever that nominal value was. And then the shaft worked, you know, in the opposite direction. The reason for that, again, is because there are tools that can create the bores that are to the standard nominal sizes, okay? When we're looking at a shaft, we can just move our tool on a lathe in and out a little bit, and we can get a different size. So it's a very different process to achieve dimensions, okay? Now, you can use the basic shaft system down here. I didn't highlight it. And that's, for instance, maybe when you get in, you know, stock that has the basic size on the shaft, then you can use that basic shaft system, but the charts are all lined up with the basic hole system, okay? And that's the one that we practice here because it's used most often, but you can find resources online and in the machinery's handbook for the basic shaft system. So let's do an example where we look at specifying a fit, and this is example problem 13.1. So if I go underneath, example 13.1 is at the top-ish of page 553. And it says here that we have a shaft. It's going to carry an idler sheave for a belt drive system. And it's to have a nominal size of 2 inches, okay? So if we look down here, they have a nice little diagram here. Our shaft size is a nominal 2 inches, and it's going to have a sheave mounted on it, okay? Now the sheave must rotate reliably on the shaft, but with the smoothness characteristics of accurate machinery. So kind of like what we chose when we did our gear design to our shafts. Specify the limits of size for that shaft and the sheave bore, and list the limits of clearance that will result. Use the basic hole system, okay, which is exactly what we have on our charts here. So they decided to use an RC5 fit, okay, RC5 fit. So if we go back to page 551, let's read about an RC5. An RC5 is a medium running fit. It's for accurate machine parts for high speeds and or loads. You know, more than an RC4, okay? So, so they have RC5 listed here. So we're going to be using this column. Now, you as the designer, you know, you might decide that yours is an RC4 or an RC6. That's okay, all right? You get to make that decision, but you want to kind of make sense of it, okay? So they chose right away, it's an RC5, okay? RC5. Now, as they said, the nominal size is 2 inches. So we'll compare back to these sizes. But what I want to do is I want to go through the process of using our chart to determine what the tolerance is on the shaft and what the tolerance is on the bore or the hole, okay, the hole. So as we look at the RC5 chart, again, 551 is the page that we're on here. Again, you could go to the machinery's handbook and you'll see that. Be careful online that whatever reference you're looking at does match the standard, okay? So, I think resources are pretty darn good online. I've never run into something that isn't right, but just make sure that it's referencing back to the standard. So in our first column of this chart, this is going to be where we're going to find our nominal size range. So we want to find where our 2-inch falls. So it falls between 1.97 and 3.15. Okay. And if we go over to, I'm going to kind of put my paper under here. We go over to the RC5 column here. We want to get the hole and the shaft. Okay, hole in the shaft. So again, these numbers are in thousandths of an inch. So I'm going to start with my nominal size of 2 inches in diameter. I'm going to do 4 decimal places. And this is going to be, I'm going to do the hole first. Okay, and then we'll do the shaft. So my hole, it says that we want to apply plus 1.8. Now remember, thousandths of an inch. So if I do 1.8, that means that I'm going to take this decimal, I'm going to go 1, 2, 3 to the left. And I'm going to have 2 zeros in front of that 1. Okay. Then I'm going to be minus 0. So this is going to be plus, and this is going to be minus 0. Okay. So now to get those limits, okay, the limits. Now this is a pretty accurate hole. I would not dimension this plus 0.0018 minus 0. Wouldn't do it. You want to put the limits on for whoever is making that. So when you dimension this, this is going to be a diameter of, you're going to put 0.0018 to 2.0000, and that's going to be your hole size. Okay, and those are the limits. And for the problem, they're asking for those limits. Okay, so for this is for the hole, so it's adding those 0.0018 and then subtracting 0. So largest and smallest hole, those are the limits. Okay, and you'll notice down here, that's exactly how they showed it for that bore diameter. Show the limits, especially when they're accurate like this. Okay. Now, the next one we're going to do is going to be the shaft. Okay, it's going to be the shaft. So here's our shaft. It's still a basic size of 2. We're going to go back to the chart. Find where we're going to be at. So shaft, 2 inches. And in this case, we're going to be minus, okay, 2.5. So this is going to be a minus, and I'm going to go over a little bit, 2.5. So again, 1, 2, 3 to the left, my decimal will be here, 2 zeros in front of that 2. And then I'm going to be minus again. It's going to be 0.0037. Now, so I have to do my, I have to use my calculator. And this is why you would not want to put these tolerances. You could say, oh yeah, I put the tolerances on there, but now somebody's gonna have to get out a calculator and figure out these limits, like what is the zone? No, do that on your drawing as a favor and good practice, because you know what you're doing. So you should get the high to be 1.9975 to 1.9963, it looks like. Okay, so those will be the high and the low limit for the shaft. And you'll see on the next page here, that should be exactly what they got, and they indeed did. And then down here again, those limits are on the shaft itself. Okay, now for the problem, they wanted to know, specify the sizes, the limits of size for the shaft and the bore, and also the limits of clearance. Okay, limits of clearance. So we could calculate that. All right, we could calculate it by taking, for instance, the minimum clearance is going to be your largest shaft, and you're going to subtract it from your smallest hole. your maximum clearance is gonna be your smallest shaft subtracted from your largest hole. But the chart gives it to us, which is nice. So right before the hole column, we have the limits of clearance column right here. Here are your numbers, okay? And you can double check them, but it gives it right in our chart here. So our limits of clearance, I gotta write them down over here. Are gonna go from 0.0025 to 0.0055. Those are the limits of clearance, okay? And that's the other thing that they're asking for in this problem. So that means that these are positive values. These are limits of clearance. So never will these parts interfere with one another or even get to line to line. Line to line contact would be a clearance of 0, meaning that your worst case scenario, for instance, could be that they're right on, okay, tapping them together, okay? But here, I always have at least 2.5 thousandths, okay? Or as much as 5.5 thousandths. That's still not big. That's still not big. That's a little bit of wiggle room that we have in there, because not only do you have to hold that for that size at that point, but you've also got to hold it over a length, right, of a bore and a shaft, you know, section, which can get a little dicey depending. Okay. So questions. Using our chart, RC fits, in this case, RC5, applying what we get from the chart to determine our limits of the hole and of the shaft. And then as we look at these, like I said, because there's limits of clearance, so when we look at our largest hole and we compare that to our smallest shaft, this is going to be the maximum clearance. So the smallest shaft in the largest hole is going to be the most amount of slop that we're going to get. And then when we compare our smallest hole to our largest shaft, this is going to be our minimum clearance. Does that make sense to everybody? And these differences between these two are exactly that. Exactly that. Questions on using this chart to determine fits? You know, sometimes when you're designing, especially when you're new to design, it is kind of like, well, what should I put on there? And that's where these types of resources come in handy. Start reading, like, where does my application line up? And if it's not on one of these 3 charts, then you pull out the machinery's handbook and you get it. Okay. So, so know that you're not on your own, or you don't have to be like, well, that one was that for forever. I'm not exactly sure why they specified it, but I'll just put that on. You don't want to do that either, okay? You want to try to make sense of it, and maybe their tolerance did line up with this, or maybe it didn't, and then it's asking like, well, why not, right? Why not? And then that's
There's
when
a
you start
question.
investigating. Yes,
Oh, there's a question in the room.
yeah,
So, just like you have clearance fits here where the RCs and it kind of tells you which one is which, do they have that same kind of chart for like finishes? Like, how do we know if a 16 finish is good enough for sliding on versus is a 32 finish okay to slide on? You know, like,
Yeah.
is there like a chart for that?
that's a good question. So just like when we were over here and we looked at our finishes and we looked at the manufacturing processes that are going to achieve those, the tighter the tolerance, you're naturally going to get a better finish. Okay. So, because when the tighter the tolerance occurs, you're going to be using more accurate machinery to get at it. So just the nature of the tolerance being tighter brings that surface finish to be smoother and smoother. Okay. But if you need something that does need to be better than that, and that again, I can't answer that definitively. It's probably going to be something that is going to be dictated by your application, your industry, the stuff that you guys do in the company. then you'll know what that's gonna be. Does that help a little bit? But naturally, so like, when you have a milled surface and you have anything that's in this level right here for any of these processes, you're naturally gonna get a 125 when you go to a finish cut on anything, which is almost everything in machining. And then anything that's better than that, well, now I'm going in and I'm cleaning it up a little bit more because I need a tighter tolerance, and you're gonna start creeping over to the 63. Okay, just by the nature of trying to achieve that tolerance. Okay, so that'll naturally kind of happen, but you'll need some guidance probably from, you know, other people in the industry or what your existing product line is. Ryan, do you have any input on that?
Yeah, I agree with that. I mean, there's not necessarily a chart, but the tighter the tolerance, the better the surface finish.
Well, like, that's fine, like I have, like at work, for example, like I'm making snap ring mandrels. So
Okay.
mandrels made to expand the snap ring, and the snap ring slides down until it hits the end of the mandrel and then falls off and it falls right into the groove, right?
Okay.
How do I know how smooth that has to be? You know, like what is too smooth? What's not smooth enough? You know, like how am I supposed to know that?
And in that case, you don't want it to catch the ring to catch on the mandrel, basically, right?
So is a 16 good enough?
So there-
Does it need to be an 8? Can it be a 32?
So there are little cards
Yep.
that have the surface finishes on them, and you
Mhm.
can feel it with your fingernail.
Mhm.
So like, that's a good way to judge it. So you can tell if this is just a turned part, I run my fingernail on it and you can kind of feel what a 32 or a 64 surface finish feels like.
Mhm.
So that's a good way to gauge it by feel.
Mhm.
Other than that, I mean, you could, for seals and stuff, like, if you look at an O-ring catalog, Parker catalog, they'll have surface finish requirements for sealing applications.
Mhm.
Something like this is more custom, where you probably want to look at, you know, something else that was designed similar in industry, or run your finger across it and do some tests with it.
Mhm.
But I think if you mill or turn something like that in a lathe, it's probably gonna be good enough for what you're doing.
So then theoretically, I guess the what I've gotten out of your guys' answer is, like, for the most part, you won't need new surface finish marks. It's mostly just let or well, unless you absolutely need it, but
Unless
let
you
the
need it.
dimensioning do the driving of the.
So like, this is probably gonna be a turn part, right?
Yeah.
Picture this mandrel.
Yeah.
So if you look at that, you can, within the turning range, you could go from 215 to 16. So in your case, if you know you need a little smoother finish, you don't want something to catch up on that, then you could, you know, tolerance a 32 finish.
Yeah.
And they could still most likely turn it, so you're not introducing a more expensive process like grinding. What you would want to do is put it way down at like an 8 surface finish, then you're gonna have to grind those parts, and that's probably overkill for your application.
Okay, cause yeah, in this instance, I looked at it and then. We had a mandrel for a different line, different snap ring and whatnot, and I just kind of copied their finishing and they went to a 16, so that's what I
Yeah.
did, but.
Yeah, so that's on the far end of turning. You might even get into some other grinding or something to finish that.
Okay, all right,
And you know, even there, BJ, just so that you know, when parts are, you know, you're expecting something to be machined. And it's not expected anymore to put a finish mark on every single feature. When it's obvious that it's a 3-place decimal and you're gonna be milling it, unless you want it, for instance, better than that, then you would want to put the finish mark on. Or let's say you're just cutting something off and maybe the length isn't functional, but you might want it to look nice and you don't want to have like a rough cut from a saw on the end. You may put on then, even though it might be okay to deviate plus or minus 20 thousandths, I just want to have a nice little cleanup on there, 125, so it looks nice. That's another case where if the tolerance is lower, like down here, on the manufacturing processes side of things, but you want a nicer finish, you know, not crazy, but you want it to be a finished finish, then you would want to add a 125. Does that make sense?
yeah.
Good.
Okay.
Any others?
A lot of time on templates, there'll be a check mark for the surface finish and a default of 125 or something too at companies. So if you just put that surface finish mark on there, sometimes it'll default to that as well.
Yeah, that's a good point too. Yeah, and then you don't have to put them all on all the time, right?
Yep.
It's kind of like defaulting
No,
to
you still would put them on, but it's just in the,
in like the notes section.
yep.
Yep,
Yep.
it would be like a blanket saying for any finish marks, they're all blah, 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 unless otherwise specified.
Right.
Yeah. Yeah, good, 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 good. Other comments or questions? All right, okay. All right, so in this example then, here was the limits of clearance, which we saw you can do with, you know, going and subtracting those values, or our chart has them there as well. And these are the exact numbers that we had in our chart. And then lastly, you'll notice the little sketch down here, just showing physically what each one of these numbers meant. The limits on the sheave, the limits on the shaft, and then the limits of clearance aren't part of your drawing, but this is where we would actually dimension them and in limit form. So it's easier for the person who's manufacturing and ultimately checking it too. Okay. All right. Questions? This is very practical stuff that you guys will use on a daily basis for sure. And it's one of the most important parts of your job for the reasons we talked about. Okay. All right. Interference fits. Okay. Interference fits are going to be when an inside member is larger than an outside member. Now, this doesn't have to be circular features. We're going to be applying it to circular features, but this can be, you know, any shape or form. And it's going to require the application of force in order to assemble it. Okay, so maybe not just tapping, but pounding, putting an interference fit together. Force fits are going to where we have controlled pressure between the mating parts, okay? And and both pieces want to, like we say, occupy the same space. They want to occupy the same space. And then shrink fits is when one member is heated to expand it, and then the other one might even be cooled so that we can actually get those together. So the heated one is going to expand out. The cooled one is going to contract so that there's some clearance there, so that as they actually come back to room temperature, warming up or cooling down, depending on which side they were on, then they will actually be together, and you don't have to use force to actually put them together. So table 13.4 on page 554 lists some common force fits or interference fits underneath here. Okay, so 554 interference fits. So you'll notice that they all have classes of FN, and class of FN1 is going to be a light drive fit. And as we go up in classes, and the maximum is going to be a class FN5, this is going to be a larger force fit. Okay, chart acts exactly the same, meaning you have your size range for whatever you're looking at, like I said, diameters or widths of, you know, whatever you're trying to fit together. And then they're going to have their column for their hole, their column for their shaft. You're going to apply that to the basic size. And then automatically you're going to end up with an interference. Notice that when we have interference here, okay, these numbers are not 0 or negative. Okay, they are going to be, you know, those are the actual values of interference that we have. Okay, this is the amount of min and max space that both parts want to occupy. As we go to the right, you're going to notice that even on this first column, these values for limits of interference get larger. Okay, because this is a larger press fit or a heavier press than over here. Okay. So again, thousandths of an inch, and then applying becomes exactly the same as far as figuring out the limits and such. We will be doing a force fit example in just a bit, so you'll get a chance to practice that. Now, shrink fits are going to be desirable when heavy presses are required. So if it involves pressing something together where we're putting it together, and sometimes it can be too much interference where you're literally damaging the materials. They might even be like, you know, like I don't know, peeling away from each other as you're trying to put them together. That's when you want to do a shrink fit. So you're gonna heat one of the elements up. It's gonna be the one that's on the outside so that it expands and the hole or the internal feature gets larger. And then sometimes again, you can cool down the internal piece if you need to, so that now when you put them together, there's actually clearance. Okay. And then you can let them get to room temperature to expand and contract appropriately so that they're going to then remain together. Now, if you want to know how much you need to heat up and cool down items, there is an equation here that's here for you to use. So on page 555, equation 13.1. This equation looks at the total deformation that's desired, okay, in inches or millimeters, depending on the units you're working in. So this is going to be out here. Alpha is going to be the coefficient of thermal expansion. So coefficient of thermal expansion lets us know how far something's going to move for every degree of either Fahrenheit or Celsius. If we go up to the chart in that same page at the top column here, for common materials, they have the alpha, or the coefficient of thermal expansion, okay? So here is the column for inches or metric, or for English units, and then metric units. Now this is how many inches it's gonna move per inch, So if I look at an inch, how much is that going to move? Now, notice these are tiny numbers. This is 6.5 times 10 to the -6. So that means from my decimal place, I'm moving 1, 2, 3, 4, 5, 6. So in front of here, there's 5 zeros. It's not moving much per degree Fahrenheit. Okay, so for 1 degree Fahrenheit that I warm that up, it's going to move 0.0000065 inches for every inch. So if it's 2 inches, we would multiply that by 2. Okay, so it's like to the unit length, So tiny little numbers per degree Fahrenheit or millimeters per millimeter per degree Celsius, depending on what you're working in. So that's going to be according to the material that you're dealing with. Then the capital L is length. So what is the nominal length of the piece? Now, if it is a circular feature, it says right here that the diameter will equal your L. Okay, so don't think, oh, I have to know how long that diameter is. No. Whatever the diameter is the L, is the size there. And then the delta T, okay, delta T, that's going to be going from your, what we call ambient temperature. So if you know what your room temperature is, okay, then that temperature difference is going to be however many degrees Fahrenheit that you need to go to achieve your deviation or your total deformation. So you can do this in one of two ways. You can either solve for the temperature that you need to heat it up to, or if you know what temperature you're heating it up to, how far is that going to deviate? Okay, so you can rearrange this algebraically one way or the other. Okay, so that's a kind of a cool equation to work with if you have an application for it. Now, as we look further, stresses for force fits. So as we said earlier, when we have two parts that are trying to occupy the same space, okay, one is going to expand and one is going to contract. And through that process, pressure is going to be created, okay? Now that pressure is going to be in compressive form on the inner part, and it's going to be in tension or pulling apart on the outer part, okay? But that pressure also directly relates to the amount of stress that each one of those parts is going to have as well. Now, the stress is what becomes important to us. And the stress is important because we need to make sure that our stress does not exceed the yield point of our material, So I'm going to go underneath here really quickly. And again, this is going to be review. I know it is because we've talked about this before, and I know the classes that you've covered this. So if I look at, a material, all materials have a stress strain diagram, right? We call that a tensile test or a pull test that we do on them. We have our stress on our vertical axis. We have our strain on our horizontal axis. And then for steel, a very typical shape is going to be something like this, right? And at this point, like right here, This is our yield point. Okay, this is our, what we call our tensile, or sometimes referred to as the ultimate strength. It's the highest point on the curve. Okay, but the yield point tells me that I have 0.2% elongation that is no longer going back. So if we go just below that yield point right here, this is what we call the elastic area, or the proportional area of our curve. And what that means is every time that I put some stress on it, it bounces back to its original shape. Okay. But then when I start to see this yield point, and this yield point, technically, this is actually failure, because now what we've done is we permanently deformed it 0.2%. Doesn't sound like much, but we have. And what happens at this point is that the internal grain structures no longer are going to perform mechanically like they did down here. Down here, that steel is the way it was supposed to act, okay? When I pull it apart, it bounces back. Pull it apart, bounce it back. We keep putting more and more on it. And then when it doesn't start bouncing back, we start seeing that. So the yield point is important to us, because anything above the yield point, this is failure. Anything below the yield point, we're okay. All right. But again, if we're at the yield point, we're technically already are seeing some permanent deformation here. Okay. Which technically becomes failure. Okay. Now you may not see it fail. We may not see a crack. We may not see anything happen, but internally to the material, those grain structures have now slipped and they're not what they were down here. And that's why we need to know the yield point. That's why we apply, for instance, factors of safety, so that we don't get close to the yield point. We end up, if it's a factor of safety 2, maybe we end up about half that distance. Okay, because we don't want to get close to it, because we know right after it we're done. Okay, so when we look here and we look at the stresses that are induced because of the pressure, we want to make sure that we always have tension and compression happening. Because if we go beyond the yield point of either one of these materials, then all of a sudden we're not getting the pressure we need to hold these together. Okay, so that's the reason for the stress analysis that we do here. We want to continue to have that tension compression occurring so that our parts remain in the state that we need them to function, okay, and not fail, right? So the procedure for calculating stresses is on pages 555 to 556, and the formulas and conditions are there. And it's gonna also reference figure 1316. So I'm going to go underneath and we're going to look at that. Figure 1316 is going to be this one right here. So we'll see that one come up. So at the bottom here, here's our procedure in this little like dotted box, and it's really nice. Now, first things that you're going to do is you're going to determine what is the amount of interference that we're going to be dealing with. Okay. And that's picking your fit off the FN chart. Okay. Then once you have your fits figured out, now you're going to calculate your pressure. Your pressure, P, is a direct relationship of the material we're dealing with. Okay. The material. Now that capital E, that's modulus of elasticity. Modulus of elasticity is directly related to, it's the slope of the line. So if I bring this back, the slope of my line in the elastic area, modulus of elasticity, is this. It's the slope of that line. Okay. Modulus of elasticity for steel is going to be like 29, 30, 31 times 10 to the 6th PSI. When we start looking at aluminum, it's going to be about half that. 15s, 12s. Bronze is about half that. 17s, 16s, 15s. Modulus of elasticity. And what that means then is that, you know, compared to the slope of the line, aluminum is going to want to move more when I pull on it. So its slope is going to go like this. Okay. It's going to be more like this as opposed to this. Okay. So it's because this strain is how much it's going to move per unit of length when I put something on it. Okay. So if it moves a lot more like aluminum and bronze, this line is gonna hint in this direction as a smaller value. Okay. Steeper is going to be a larger value. Okay. I'm sure in your strength of materials class, you'll be covering that. Or you did cover it. You did cover it. You guys have had that. So, let me go back underneath here. I'm still over here. So that's modulus of elasticity. That'll be given to you for your material, or you look it up based on the qualifications. Then this deformation here, this is going to be the amount of interference physically that you have between the two parts. And then these A, B's, and C's are going to correspond to the radiuses of the two parts that are together. Okay, so A is the radius to the inner ID. B is going to be to the surface that is of, interest. This is the one that where the interfering is happening. And then the outside is going to be to the outside member. Many times these are called bushing on the inside and sleeve on the outside. But this can be any elements. It can be, like I said, we're doing it in terms of like round things. This could be a solid shaft where we're going to be pressing on a gear. We could do that. Okay. So it's just really inner portion is the bushing. And then the outer is going to be the sleeve, but these can be different types of elements and they don't have to have an inside diameter. If A is solid, then A would be 0 in our calculations. Okay. So these are the radii, the A, B's, and the C's. And then 2 and B is on the bottom. So those are the variables that go into determining the pressure. Okay. Now, this is the pressure when we have one material for both. So if both the sleeve and the bushing are steel, then we use the top one. But many times our bushing is something different. A lot of times it's going to be maybe bronze. And then the outside is going to be steel. So just depending. So if that's the case, then we have to take into consideration very similar equation, but this time we have two different materials that we're dealing with, one for the inner and one for the outer. That's what the I and the O are. Okay, and that's the modulus of elasticity for each, and then the same A's, B's, and C's. Okay. So you'll notice that they give you all the items for what each one means. Now, the other one that's on here, maybe I missed it when I looked at it. It was on the second one. They didn't have it in the first one, but on the second one, you'll notice that they have these like cursive VO and cursive VI. That's Poisson's ratio. And Poisson's ratio, as you guys know, is going to be how that material reacts when it's being pulled on. So Poisson's ratio identifies, as we go along, the length of something that's axial strain. But then that axial strain has to come from somewhere. So naturally what happens if I have a rectangular piece or square or whatever, it can be round as well, and I pull on it, okay? I pull this forward, I pull this back, okay? And I elongate it. What's gonna happen is this is physically gonna get longer, right? This is what my deformation would be. Now that has to come from somewhere, and different materials react differently. So if I'm pulling this along, that means that this distance, this original distance, is going to get smaller, both in the width and in the height. Okay, and Poisson's ratio is that ratio to axial stress to what we call, or strain, axial strain to lateral strain, how much that gets smaller on the other dimensions. That's Poisson's ratio. Okay. And like I said, I know that that's review for you guys. Whoopsie. You go back underneath. Okay. So that's what the little V's are, Poisson's ratio. It'll be given to you when you need it in the problems. If you need to put it in, if it's not given, just use 0.27. That's a very standard number because a lot of metal materials react very similarly in those two directions. So when in doubt, use 0.27, and I have that on the chart as well, or on the Excel spreadsheet. And then that's going to compute the pressure. Now, to get the tensile stress, we're going to use that pressure, okay? And on the outer member, we're going to use the C and the B dimensions. So you're going to notice here's there's C to the outside, the radius, and then B to kind of like the surface of interest where the interference is occurring. And then for the compressive stress on the inner member, we're going to use that very same pressure, but negative this time. Compression is gonna be in the opposite direction, so tension is always gonna be a positive stress. Compression is gonna be a negative. You would have, again, seen that in strength and materials. And that's that same thing here as we see it. Then if you want to know what the actual increase in the diameter of the outer member was at that place, you can calculate that. And then what the decrease in that inner member was. Okay, and those are the equations. So now some of these, and especially when we look at having two different materials, you can see that calculating the pressure here is kind of nice to have like an Excel spreadsheet to do that. And we do. Okay, we will use our Excel spreadsheet to walk through a problem similar to this. Now, these aren't hard equations at all. So if you wanted to do it manually, you certainly can, but you don't have to. So let's look at example problem 13.2 and walk through this. And what I want you to do is have at the ready the spreadsheets for those force fits, okay? Because we'll exercise those as we go through. And you'll see how it works with a problem similar to this, which will also mimic what you'll be doing for your homework. So here we have a bronze bushing is to be installed in a steel sleeve. So using the illustration up here, the bushing is on the inside. It's going to be a bronze material. And on the outside, it's going to be a steel sleeve. Okay. The bushing has an inside diameter of 2 inches and a nominal outside diameter of 2.5. So what that means is the inside, our A radius, is going to be half of 2 inches. And then B, which is the 2.5, is going to be half of that. But that means that the 2.5 diameter is our interfering surface here. This is what we're interested in. It's going to be the common one between the sleeve and the bushing. Okay. Then the steel sleeve has a nominal inside diameter of 2.5, the same size as the bushing, and an outside diameter of 3.5. So what we want to do is we want to specify the limits of size for the outside diameter of the bushing and the inside diameter of that sleeve in order to obtain a heavy dry fit. We're going to use an FN3. Okay, so they're giving us the class of fit, and we're going to use the chart to determine the limits of both the sleeve and the bushing at the 2.5 inch diameter. And then it says determine the limits of interference for that result as well. Now, for a maximum interference from part 1, we want to compute the pressure. That's the worst case scenario. The maximum amount of interference is going to give us the worst case scenario. But if it's anything less than that, anything less interference wise, then it's just going to be less pressure, less stress. So we want to check our worst case scenario. Okay. So the stress in the bushing, and then we also want to know what the deformation is on the bushing and the sleeve. So how much is that bushing going to get smaller on that dimension, and how much is that sleeve going to get larger on that dimension? Okay. It gives us our modulus of elasticity for steel and for the bronze. And then it tells us that our Poisson's ratio is 0.27 for both. Okay. So first things first, we're going to do number 1. We got to specify the limits of size. The limits of size. Now, let's take a peek at our spreadsheet and kind of look at kind of how this is set up so we can make sense of what we're gathering here. So on the spreadsheet, we have a whole bunch of inputs to put in here. We're going to first start with putting in our nominal sleeve OD. Okay, the sleeve OD, this is on the very outside. So if we go back over here, that's outside diameter right there. And it said our sleeve has an outside diameter of 3.5 inches. So I'm going to put on here 3.5. Okay. Then I've got a nominal bushing ID. Okay. So the inside diameter of the bushing, that's dimension, it's the inside diameter. Don't put A in there. So that's going to be our 2 inches. 2, enter. Okay. Now notice what happened already. Down here at the bottom, the green are populating. So our A is half of the 2 that we just put in, and our C is half of the 3.5, okay? So you want to put the diameters in here. And then the nominal size of the bushing OD, that was, that's the 2.5. And that's going to be, again, the surface that's common, oopsie, 2.5. That's the one that's common between the sleeve and our bushing. Now, class of fit, they're giving our class of fit to us, so we want to put in here FN3. And now we're gonna go to the chart and we're going to find the maximum limit on the bushing and the maximum, or the max and min on the bushing and the max and the min on the sleeve. Now, before we go here, the chart calls out hole and shaft, hole and shaft. So when we're talking bushing and sleeve, our hole is going to be on the sleeve. Okay, so I'm going to put hole here. And our bushing is going to be the shaft. Okay, because if we look at this surface right here, this is the internal part, that's the shaft, and this is the outside part, that's the hole on our charts. Okay, so we want to now go there, and our nominal size that we're going to be working with is going to be the 2.5, the 2.5. Okay, and again, these are all filled in for us already, so that's nice, but we have to fill in our limits because that's part of this problem. So let's go underneath and go to the FN charts, and we've got FN3 right here. So we want to find our dimension of 2.5, 2.5. So we're going to go down, down, down. Here's 2.56, so it's going to be the one just above. Okay. And now it's gonna be these right in here. I'm gonna zoom, zoom, zoom in so we can see them in case you don't have a book in front of you right now. So for our bushing, which is the hole, okay, we're gonna have a diameter of 2.5 as its nominal size or its basic size. And on the hole, we're gonna add 0.0012 and subtract 0. Okay, which means then our limits are going to be 2.5012 and 2.5000. Okay, those are the limits. So this would be our max and this would be our min. Okay, that's for our hole. Now we're going to do the shaft. Okay, the shaft is going to be this column right here. Okay, and it's going to be these two numbers. So on our shaft, you still see that, and this is going to be our sleeve. Okay. Diameter again of 2.5000. So this is going to be plus 0.0032 and a plus 0.0025. So the limits then are going to be 2.5032, 2.5025. Okay, and this would be our max, and this would be our min. Okay, and you want to check here, just make sure that your sleeve or your shaft is bigger than, oh, did I do that wrong? I did it wrong. My numbers are okay. I've got to relabel. I'm so sorry. My shaft. This was the hole that stays there. This is the sleeve. I'm so sorry because I was like, it's not looking right. This is the bushing. I'm so sorry. My bushing is the bottom because this is the shaft that's fitting inside of the hole. My bushing has to be bigger on both sides than my sleeve. I'm so sorry about that. Everybody got that switched out. So your hole is your sleeve. We already identified that. I don't know why I didn't follow through. And my shaft is my bushing.
Have to add more donuts to the party.
Yes, yes. We got to figure out when we're all coming and going to be on campus, right? Before we're done. Okay. All right, so we have those. Now what we're going to do is we're going to fill those into our spreadsheet. And let's see if I can screw this up too. So this is going to be the max limit of the bushing OD, the max limit of the bushing OD. So that was our second one. So that was 2.5032. The minimum 2.5025. Then our maximum limit on our sleeve ID. So that's going to be 2.5. 0.012. And then our min is gonna be 2.5000. Okay. All right, any questions so far? Now, you'll notice that, like we had pointed out already, it did our radiuses for us, but now we need to know what is our total interference. And this is the max limit of the interference. Now, you could do the subtraction up here if you wanted to, or you can go to our chart and pull it from the chart. Or again, you could do the subtraction. So if we go back to our chart, I guess I always did it this way. My maximum interference, according to my chart, and you would, even if you calculate it, you want to double check it. My maximum interference is going to be the larger of these two values. So if we go up to the top here, this is our limits of interference. It's getting sunny here, I guess. And my larger value is the 3.2 or 0.0032. There we go. Okay. Now, the next thing we're gonna add is the modulus of elasticity for the outer member, which is the steel, okay? The steel is 30, 1, 2, 3, 4, 5, 6. So it's 30 with 6 zeros, 30 times 10 to the 6th. And then we've got our modulus of the inner member. It gave us to us in the problem. If you need to look back, I know it. I'm pretty sure it's this. I better look myself, but it's 17 times 10 to the 6th, or 17, 1, 2, 3, 4, 5, 6. Enter. Okay, now it's starting to fill some things in, right? But we do need to add our Poisson's ratio because we have the two different materials. So it's going to be 0.27 and
It's in the
0.27.
problem statement,
There.
but it should be in the appendix in the back.
Is that? Where?
All right.
That's in the appendix in the back, right,
What's that?
Kelly?
modulus
Modulus
No,
elasticity,
in this
please.
problem, it actually gave it to us. It
Right,
gave
they're
it to
asking
us.
though, if it's not given, it should be in one of the appendix.
Oh, yeah, then you would know your material and you would get it. Yes, yes. So
It's probably
there's a
in that
good list in the
appendix
back of the book that has it, but there's also, you know, you would have resources from your, you know, material manufacturer or supplier.
Yeah, we're just trying to see if it's listed in one of them.
If you look, in the back, on that one longer one, so if you go
Oh,
to,
here it is.
know exactly where it is. So if you go to appendix 3, I'll go back underneath my camera here. Hold on, let me just put my. Yeah.
Oh, I
we go.
see.
If you go to page 788, okay, page 788, appendix 3. Oopsie, hold on. That out of the way. And you go all the way down to the bottom of the chart, okay, bottom of the chart. It says down here, modulus of elasticity is 30 times 10 to the 6th PSI, because these are all steel. Okay. If you look for bronze, there's some other charts here as well. As you look, I know bronze, because I was looking earlier too, just to be sure. In appendix like 10, see 10, this is die-cast aluminum. There's modulus of elasticities listed here as well. Steel, it'll differ once in a while, depending on, you know, the grade of steel, but steel is always 30 times 10 to the 6. That's like gold. That's like the number. Okay. And then other materials can be different as well. All right. Okay. So as we compare then our results to what we have here, you should see that they match up with exactly what the book has. So it calculated the pressure for us first in that process. And notice that's in PSI. And then it used those two equations for the inner and the outer to get the tensile strength, or the pulling apart, the tensile stress in the outer member, and then the compressive stress in the inner member. That's why we've got the negative there. Then the increase in the outer member's diameter at that 2.5 diameter, at that mark where they're trying to, you know, interfere with each other. And then the decrease in, or the compression that's created in the inner member. Okay. And again, if you compare You'll notice that those numbers are exactly what we have, you know, in the example as well. Okay. Kind of go through. So this is very similar to, I think it's 2 problems that you guys are gonna do and walk through for your application problems. Okay? So any questions using the spreadsheet, determining the values up here, using the chart to determine the min and the max values for bushing and sleeve or hole and shaft.
So is this the value that is needed to push them together?
The stress or the your stress just has to be less than your yield strength.
Oh, yes, 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 that's a good point. Yep, so what we can do is we can then go to the back of the book. And you're gonna notice that. Now, they don't tell us in this problem, and this is something that I wish they would give a little bit more detail. So if we go to the back of the book. And we go to Appendix 3, for instance. And that is on page. The problem wasn't asking to compare it to the yield, but you always want to. So thank you for bringing that up. You'll notice that we have a column for yield strength here on kind of those carbon steels and alloy steels. Now, they didn't tell us what kind it was. All right. So as we look at the top here, these are kind of your basic cold rolled steel, hot rolled steel, kind of out of the mill, that if they're just saying steel, I would expect to be right up here. And really more specifically, probably the 1020, 1040 at the most. You'll notice that your numbers of your yield strength are far in exceeding the stresses that we saw on either one of those parts, okay, or for that steel. Now, when we do a pull test, yield strength is always going to be in tension, okay? So in this case, our steel sleeve is in tension, but the beautiful thing about steel is that it can reverse load, and I've mentioned that before. So almost identically in compression, it has the same values for yield, okay? So that's why it's one of the most widely used materials, one of the really good reasons. Now you can do that very same thing for bronze. And this one too, they didn't give us the grade of the bronze. So we have to make a little bit of an assumption here. So if we look at, let's see it. It's Appendix 12. Appendix 12. And this is on page 799. And they have properties of bronzes, brasses, and other copper alloys. Okay. Now, here are your bronzes, okay, in here. Okay. And what I looked for, because the book gave us a modulus of elasticity of 17, right? I got 15s, 14 and a half, 15. I've got 18 and 16, okay? So when we have 18 and 16, as we go over, we're going to see the yield strength is 17 for the 16, but then it goes up for the 18. So our 17, I have to believe, is somewhere between 17 and 25, right? Right? Maybe halfway in between. I'm not exactly sure, but that's how I kind of determined that one, because again, it wasn't given to us and they didn't give us the grade. And when we look at the stress on the inner member, it's 16,000, and there too, you can expect the reverse loading to be about the same.
So then is that just saying that when we press these together, they're not going to deform?
I'm
They're-
sorry, repeat that.
The question was, when you press these together, are they not going to deform? I
Oh,
mean,
they'll
they-
deform.
they'll
They'll
deform
deform.
with
That's what
those numbers.
this is telling us to deform. But what it's telling us is that we're going to maintain pressure. We're not beyond the yield point of the material. So we haven't exceeded, the grain structure is still intact in order to keep these together. That's where we're at when we
Yeah,
compare to that yield
Haven't gone
strength.
past the yield point.
Got it. Okay, that makes sense.
So if you took them apart, theoretically, they should spring back to the original.
Correct,
size.
correct. Yep.
And I think the other question BJ had was, so there's that pressure value of 3518, can you actually calculate the force required to press these together with that? I'm not sure if you can you? Kelly? If you just.
I
force
have to
equals-
believe that's gonna be a function of your press, right?
Yeah,
you
I mean, unless
could,
you can just
could.
do,
The other thing that you can do, and depending if it's a little bit more than what you believe you want to press, because again, if it's too much, you can literally peel away those surfaces, right? Now you're damaging the actual part, which was defeating the purpose. What you could do is you could heat one of the members up and then cool it and then put them together.
yeah, and I think there is a way to calculate that force too. Just if they don't show it in here, I don't
They
remember.
don't show it in here, but I think it's also gonna just depend on your press. Because your press is gonna be, you're gonna,
Yeah, you should be able to back calculate an actual
yeah.
required.
Yeah.
Cause
well,
you would need, you would need to know how long it is so that you can find out what your, square inches are that you're over the, you're distributing over, right? And then you could, yeah, calculate for the force that would be required and then see if you have a press that could do that. Yeah, you could. It's kind of like the ribbon of, I call it the ribbon of area where those two would be together. So you could find how long of a section that would be, right? How long, because that pressure is being distributed over an area around the circumference. Because the longer that
Right.
is, it's gonna take more force.
Yeah, you can
Yeah.
calculate it. I
Yeah.
just-
Yeah, they don't have it here, but that's a good question. All right. So I believe as we look back at, are there any questions on this example on the results or what they mean or any of the variables above? Okay. So let's go back to our PowerPoint. We looked at this and the very last section, which is kind of a little section here. I don't know. It's pretty it's pretty basic. I'm gonna go back underneath here. There's a section on general tolerancing methods, okay? And all that this is, I'm trying to get my thing out of here. I don't know where this one's coming from. You're gonna notice that this section just talks about and reviews when you have a drawing, you're gonna have some ability to have some standard tolerances. So again, that title block tolerance is gonna dictate when you specify dimensions without a tolerance. It's gonna default to what's in the title block. And these are some examples of, but you would always look to your specific company or at WCTC, what ours are saying. And then if yours can fit within that category, great. Then you don't have to worry about putting a tolerance on it. So that dimension has a tolerance and it will always default to whatever the title block says, okay? And again, I can't emphasize enough, you never change a title block tolerance just because, oh, I didn't use those on this drawing, okay, ever. And it might seem like, yeah, that doesn't make sense, but I don't know, it can escape some people sometimes. And then everybody's favorite, at least my favorite, is the application of GD&T as well. And so GD&T we are going to use whenever it is applicable. Now, GD&T is not a standard by itself, and sometimes, and we actually treat it that way, even in in the program that I was in before, and the way that we do it here, we have a different class for GD&T, which makes it sound different. GD&T is part of the standard, the dimensioning standard. It's just the rules of applying it, and it's a lot of times it's not the intuitive dimensions like the rectangular coordinate dimensions are. So form, for instance, we don't always put on because our size tolerances give us form automatically. It's when we want to refine on it, we're going to add things like straightness, flatness, cylindricity, and circularity. Profile, we can control dimensions, really just like our pluses and minuses, locations and size with profile as well. And then we can start looking at, profile came into the standard early on with one purpose, but it's evolved into something else. So profile early on was kind of taking care of things that were, had a lot of contours and stuff. If you look at your dashboard in your car, Can you imagine making a drawing for that where profile could be like, all right, on this basic, theoretical profile, now I'm gonna attach a tolerance, whether it's the same on either side or if it's different, we can control that. But it's evolved into, you can apply it to flat surfaces or rectangular types of parts or circular parts too. It really is very versatile. So you've got your profile there. Orientation, this is again a refinement on your size and your location dimensions can control orientation, but they have to get very close together and so orientation we apply when a refinement is needed on the size and location that's allowed. But location dimensions should all be done with position tolerancing because you get the bonus and you also get the full sweep of the radius of the full acceptable tolerance. Now, I didn't teach you guys GD&T, and I'm certain, I know Phil was very thorough in that. Did he also mention about location? When you use position tolerance, it really should be used on all locations. And you don't see it all the time. Companies that know GD&T will, but companies that don't, unfortunately, will just try to control position with your rectangular coordinate dimensioning. And you get more tolerance, acceptable tolerance area when you use location. Do you guys remember that circular tolerance zone as opposed to a rectangular tolerance zone? Maybe, maybe not.
Very little.
Is that a no?
Yeah,
Okay,
questionable.
let's do it really quick. Certainly quick. And when I do it, you're probably gonna be like, yeah, I think, yeah, we did go over that. So for instance, if I have a nominal value here, okay, and my nominal on maybe a whole location. And the location, the position is giving me the option to be plus 5,000. This is my nominal value, okay, of location, position, all right? So in the X direction here, I can overshoot it this much. I can be shy this much, okay? So this is my plus or minus. So let's say that this plus or minus is 5/1000 of an inch, okay, both sides. And then I can do the same vertically as well. I can have a plus and a minus. So I end up with a rectangular coordinate dimension, okay? Here's my nominal this way. I can have a plus 5/1000 and then again, a minus 5/1000 of an inch in both directions. So when I have a rectangular coordinate dimension, I have a rectangular or a square tolerance zone, right? Now, when I have that, okay, I will accept on +5 and +5. So this corner, right? And that'll be an okay dimension for me. If I can do that on this corner, and I can do that on this corner, I can do that on that corner. Now, if this dimension right here, if I can calculate that, right? What is that radius on the tolerance? So this is a right triangle right here, right? One of its legs is 5/1000. The other leg is 5/1000, right? 0.005. Tell me what this radius is. What is that radius? You guys all have calculators. How are you going to calculate that? You want to use Pythagorean's theorem. You've got the two legs and you want to find the radius, right? So my radius is going to be equal to the square root of 0.005 squared plus 0.005 squared. Okay. So tell me what my radius is. Everybody should be doing it.
0.071.
Tell me again.
0.0071.
No,
0.0071, and that's inches, right? Okay, so let's go up here. This radius right here that came across, that's 0.0071, right? 0.0071. Now, I will accept on +5, +5. I will accept that's going to be the same radius to here, and to here, right? But if I do 0.0071 and I land right here, what am I gonna do for the location of that hole? Am I gonna accept or reject? I'm gonna reject, because this is plus 5 thousandths and I'm up here, right? If I go over here and I have that same radius of 0.0771, accept or reject out here? Reject, 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 reject on all of these radiuses, any of those spots. But will it work? If it worked here, if it worked here, if it worked here, it's gonna work at all of those places. When we do rectangular coordinate dimensioning, we are leaving on the table, believe it or not, 53% acceptable tolerance zone that we are rejecting on potentially. That's why when we have circular features, we do not use rectangular tolerance zones. When we have got stuff like this and we know this is working, we convert it to position tolerance to take advantage of the fact that we are going to gain an acceptable tolerance zone of 53%. So my whole point there is we want to be putting position when we're locating, especially hole patterns, features that are, located from, ends of things. They should have position on every single one of them. You need to be considering that. And then applying your, your tolerance based on, is it a fixed or a floating fastener application, right? Okay. So like I said, it talked a little bit about GD&T and their application. So position, location, you should be doing this all the time, all the time. Orientation, profile should be considered most of the time with sizes and the outsides of things. And then form is going to be as needed as well as a refinement of. Concentricity in the new standard, they don't have it here. Concentricity is no longer in the new standard. I'm sure you guys learned about that. You'll see it on old prints, so you've got to know what it means. It's axis to axis. Run out, you always want to check too. If you have a concentricity, you want to be sure that you're not accidentally checking it like run out or applying it like run out. So, so you always want to kind of in this zone right here, kind of be careful or double check. Okay. So that's kind of the end of the chapter. No questions that I have in the application problems on that, but it's just kind of pointing out, like, don't forget their standards. And when you put your stuff on your when you put your tolerances on your drawings, all of this stuff is, on the table and available. Oh, Eric said, yeah, we did that. Okay, cool. Cool. Excellent. I knew Phil would. I knew. All right. So that takes us to the end of our chapter. Okay, so what I'm going to do is I'm going to stop the recording here.